Rahul, you're ready, right?
Good to know video.
Huh?
It might be good to Rahul's video on the right hand corner. Yeah.
Rahul, you can hear us, right?
Yes, yes, yes.
All right. So, yeah, I mean, Rahul is a friend of the department school. He has been here several times. And the product of the school, as we were just discussing, who are the people who are still around, who were with Rahul here, and there are many. So anyway, it's a great pleasure to introduce Rahul. We share a lot of interest, including films. Okay. Anyway, but yeah, I mean, yeah, we also share many research interests. And Rahul is going to talk today about commitments are equivalent to statistically verifiable one-way state generators. Off to you, Rahul.
Okay, thank you. Thanks a lot, Arkadev. Okay, so hello, everyone. Yeah, so this is joint work with Rishabh, who is also at CQT. Okay, so let me begin actually first by showing I should share something else, which is this. Can you guys see this microcrypt zoo?
Yeah.
Okay. So here is a zoo. Okay. What happens here is let me see if I can make it smaller. It's not possible. Okay, so in the quantum case, we have a bunch of primitives, right? So as you can see in the zoo, there's a whole lot of primitives here. And what are these primitives? All these primitives are the ones that are implied by one-way functions, okay? These are quantum secure one-way functions, OWF. Okay, now, why do we have, all these primitives lined up from top to bottom is because what happens in the quantum world is, like in the classical world, one-way functions are known to be equivalent to many things, to bit commitments, to pseudorandom generators, to pseudorandom functions, and so on. Now, in the quantum case, what happens is that if we consider equivalent of pseudorandom generator, for example, that's like this object, what is known as pseudorandom state, okay? Now, what is known is that there are these oracle separations. So these red lines imply oracle separation. So there is an oracle world where even p is equal to np, okay? So if p is going to be equal to np, then one-way functions will not exist. But these objects, pseudorandom states, may exist, okay? So there's a whole lot of these primitives, and these arrows means, this primitive implies this primitive, and then these red arrows means that they're sort of oracle separations, okay? So as such, a task at hand for quantum cryptographers is to sort of color this graph, okay? So, which means that, if, okay, here, there are a bunch of these primitives, which are all green color. Green color means they're all equivalent to each other, okay? There are a bunch of primitives here, the red ones, which are equivalent to each other. These brown ones are equivalent to each other, and so on, okay? So ideally, one should be either able to, show, like, divide the whole thing into equivalent classes and show that, a bunch of primitives are equivalent, or that there is separation between these equivalent classes, right? Now, the thing that we'll be talking about today is this implication here between EFI and one-way state generators, okay? And in fact, what is written here is sv-OWSG, which I will refer to as sv-OWSG, and I'll describe what this IV or SV actually means. Okay, so this is sort of the motivation at this point to mention as to why we consider these primitives in the quantum case. And so this is basically some kind of a cryptography that people sort of say that, oh, some quantum cryptography may be possible even when one-way functions may not be possible. Okay, so that's what it is. And this 1PRS is what I will refer to later. This is sort of an equivalent, quantum equivalent of pseudorandom generators. Okay, and these OWSGs are quantum equivalent of one-way functions, not quantum secure. So there are two things. One is quantum secure one-way function, which is OWF, and another is OWSG, which is a quantum one-way function where f of x itself is a quantum state. Okay. Now, in a quantum secure one-way function, x and f of x both are classical. Just that the adversaries are allowed to be quantum. Whereas in a quantum one-way function, x is classical, but f of x is quantum. Okay. And these are the objects which are potentially weaker than one-way functions. And much of quantum cryptography is still possible using these objects. For example, one-way state generators imply this EFI, which imply commitments. And in the quantum case, commitments imply oblivious transfer, which implies multi-party functionality. Okay. So it's possible to, get multi-party functionality, sort of almost at the lower end of the graph here. Okay. And in middle of this graph is this pure OWSG, which is, a quantum one-way function where f of x is a pure state. Okay. All right. So given all this, let me go back to my slides.
Rahul, is this a picture to sort of imitate Impagliazzo's worlds in the quantum setting, or?
Yes, exactly. This is the picture that sort of imitates Impagliazzo's worlds, but here there's a whole lot of world at this point. I mean, it's not any clean 5 worlds or anything, right?
Oh, no, but you believe in the multiverse anyway.
Exactly. We live in the multiverse anyways, exactly. So, all right.
Multi-universe is multiple.
Universe is one.
Okay, so I'm back to the slides. Can you see the slides?
Yeah.
Okay. All right. So commitments, as many of us are aware, are fundamental cryptographic primitive, right? There are two parties, a sender and a receiver. There's a commit phase in which the sender commits to a message M to the receiver, and there's a reveal phase where the sender reveals the message M to the receiver, right? And we want hiding, that is, in the commit phase, the receiver should not be able to figure out M, and binding, that is, after the commit phase, the sender should not be able to change M, right? So that's commitment. And okay, so now what are one-way functions? So we are aware of, classical one-way functions. They should be efficiently computable in the forward direction, and they're hard to invert by efficient, potentially non-uniform. I mean, we can consider often non-uniform PPT adversaries, which are probabilistically polynomial time adversaries. Okay. And they are known to be equivalent to commitments, pseudorandom generators, pseudorandom functions, and so on in the classical setting. And quantum secure one-way functions are the ones where basically, as such, they are classical functions, okay, efficiently computable, but hard to invert even by an efficient non-uniform QPT adversary, okay? Now, as I showed you in the graph, there's a lot more that's possible in the quantum world. And yeah.
When you talk about quantum secure, you said the function is classical, but it's When you said it's efficiently computable, it's efficiently classically computable or efficiently computable in the quantum world?
No, efficiently classically computable.
Okay, so
I mean, the vanilla version is efficiently classically computable. There are other versions where you allow forward computation also to be quantum, but still X and F of X are classical.
okay.
So these are much harder objects,
Yeah.
much more difficult objects to construct.
Sorry, what?
This quantum secure one-way function that you said, I think they are more difficult, more generalized objects than just classical one-way functions.
Yeah. Okay, so now let's get to quantum one-way functions, okay, which are also referred to as these one-way state generators. So here, essentially what we have is the f of x is a quantum state, okay? So now there are a bunch of, basically an OWSG is defined using a bunch of algorithms, okay? So one is key generation, okay? So key generation just generates X, okay, which is supposed to be the input, right? Now this is an efficient algorithm. It generates a classical key X, okay, classical X. Then the state generator generates f of X, which is psi of X, okay, here, or phi of X. Again, it's an efficient algorithm, okay? And then there's a verifier, which does, accept or reject. And what it does is, so X prime is what is supposed to be given by the adversary, and then verifier decides, whether to accept X prime and another state or not, okay? Now, key generation and state generation are efficient. However, verifier may or may not be efficient. So there are two versions. One where verifier is efficient and one where verifier is not necessarily efficient, which is referred to as statistically verifiable OWSG, okay? Which was also written in Satta's graph as IV, as inefficiently verifiable OWSG, okay? Okay, so what is the deal? What we require is correctness. One that, okay, X is generated by key gen, then phi X is generated by state gen. And if it is a valid X and phi X, then the verifier should accept, okay? So the probability that verifier accepts a valid X and phi X should be like close to 1. And security, for any QPT A, right, what do we want? We want that once X is generated and phi X is generated, and A is given these M copies of phi X, okay? M copies of phi X. So in the quantum case, this M copy is also important. In the classical case, adversary was just given f of X and that was good enough, right? Multiple copies are not needed, or if needed, adversary can generate it itself. However, here we need to provide those copies. So we provide these M copies. And then X prime is returned by the adversary, and then the verifier must reject X prime and phi X, okay? Okay, and one can note that this verifier needs this one additional copy of phi X to verify, okay? So M copies are given to the adversary, but those are gone because they're given to the adversary, and verifier needs one additional copy to verify. Is the definition clear? And by the way, questions are welcome in between.
Phi X is a density matrix. It's a state.
Phi X is a state, quantum state, yes.
A density matrix. That output of state gen is a density matrix, or?
Yes. It's not a density matrix written down, but it's a quantum state in a quantum register. I mean,
okay,
right? Okay. Yeah.
I don't follow. So what do you mean by phi X tensored M times? So is it just
it's just M copies of phi X. M independent copies of phi X.
Is it M copies of the same phi X or M copies you're generating it, doing this generation process m times and outputting.
No. See, generation happened once. Okay. Generation happened once. So the state gen generated this X, right?
Yes.
State gen generated this phi X.
Yes.
But then, state gen. So yeah, using the same X, the state gen will generate like m copies of phi X. Let's put it that way.
How do you manage to do that in the? So I understand you want m copies because you want to give the adversary ability to possibly look at it multiple. How do you even manage to get m copies of the same state?
No, state gen on input X generates phi X, right? So state gen will run this thing for state.
Yeah, it's a unitary operand. There's no measurement, nothing to the map.
Okay.
It's a unitary.
So it will just run. Okay.
Okay.
In fact, phi x therefore is a pure state, right?
No, phi x. Okay, if it is a pure state, then it is called pure OWSG. If it is a mixed state, it's called OWSG. So there are two versions of this quantum one-way functions where phi x.
I can think of state gen as some fixed unitary operator, right?
And then
No. It need not be unitary. It can be a like a CPTP map, for example.
So CP, yeah.
Okay. Okay.
Okay.
Okay.
No, but if you trace it out, then
every CPTP map is embedding polarity thing, do a unitary, remove the maps. We remove some maps.
So that's my question is, are you to get the m copies, you just run this state gen m times, but these will be like m different samples.
See, even in the classical case, right? Prahlad, even in the classical case, right? You can think like that there is a PPT algorithm which given X generate a kind of a distribution P, right?
Yes.
So now you run that PPT algorithm again and again on the same input X.
Yeah, fair enough. Got it. Sorry for the confusion.
Yeah. Okay. All right. Wait a second. Something is.
Can you jump a slide?
Oh, something is not working. Give me a second. My screen. Okay.
we are seeing a fresh screen, a fresh slide.
You guys can now see which slide actually?
Yeah,
OWSG.
Yeah, okay. So now you're seeing this EFI slide, right?
Yeah.
Okay, now EFI is basically E. So E stands for efficiently sampleable, F stands for statistically far, and I stands for computationally indistinguishable. Okay, so it's sort of a pair of states, rho 0, rho 1, which is generated using this state gen, right? On input B generates this rho B. And what we want is that rho 0 and rho 1 are, computationally indistinguishable, and they're statistically far, right? So that means this L1 distance between rho 0 and rho 1 is, say, some noticeable function, okay, in lambda. And such a pair is called an EFI pair. All right. Now, so there is one more thing I'll have to define for technical reasons, which is this called as this imbalanced EFI. Okay. What is that? That is basically a generator which takes the string S as an advice string. And S star imbalanced EFI is such that for all S which are less than equal to S star, rho 0 S is computationally indistinguishable from rho 1 S. And for all S greater than equal to S star, rho 0 S is statistically far from rho 1 S. Okay. Now we'll see why we need this kind of a slightly weird object, but we'll need this later. Okay. All right. So as I had already mentioned, motivation using that Satta's graph, right? That there are a whole lot of these primitives, and we need to find out, for example, what is the relationship between previous like before our work, Khurana and Tomar, right? They had shown that pure OWSG, right? So OWSG with pure state output, where phi of x was pure, implied EFI, okay? And EFI are known to be equivalent to commitments, okay? And which commitments are known to be equivalent to oblivious transfer and multi-party functionalities. So this was known, but the question of whether a mixed state OWSG will imply EFI or not was open. Okay. All right. So after our result, the updated scenario is as follows. So we of course have one-way functions imply pure OWSG, but then there is a oracle separation, this red dot. So there's a oracle world where pure OWSG exists, but OWF do not exist. Okay. And now pure OWSG, of course, imply OWSG, and OWSG imply statistically verifiable OWSG. And what we show is that the statistically verifiable OWSG are equivalent to order n over log n copy statistically verifiable OWSG, okay, which are also equivalent to EFI. So it is this order n over log n copy is there. So now the question is, how about lesser number of copies? So what is known is, now pure OWSG and SV pure OWSG are just equivalent because the verifier there can be efficient without loss of generality using swap test. And now pure OWSG imply small O of n over log n copy pure OWSG, which is shown to be so these objects, which are the small n over log n copy pure OWSG, are shown to exist unconditionally. Okay, so these objects exist unconditionally, so they cannot imply EFI unless EFI also exists unconditionally, right? So at this point we have this sharp sort of a division, that is big O of n over log n copy sv-OWSG imply EFI, whereas small O of n over log n copy, even pure OWSG, are unlikely to imply EFI unless EFI exists unconditionally. Okay. Right. So what we're going to do is we're going to show a construction of these imbalanced EFIs from sv-OWSG, and using known construction from Khurana Tomar, imbalanced EFI will imply EFI. Okay. So what we will look for is essentially this construction of imbalanced EFI from sv-OWSG. Okay. All right. Any questions?
Rahul, so this n over log n.
Yes.
What's the significance of that number? N, is it because of the hybrid argument gives an n is the same coming from there, or is it a different n?
N over log n copy. Remember the m there, the number of copies that we have to give to the adversary?
Yeah.
That's n over log n.
No. But where does this not? Why is this a natural sort of?
Yeah, where does this number come from, right? Now, even in the classical case, right, I think it is known that in order to get, say, pseudorandom generator from one-way functions, you need at least n over log n invocations of the one-way function, right?
And which part of the argument uses that? Is it the number of times you have to do the hybrid argument, or is there somewhere where is this number of invocations come from?
Okay, this basically comes from the fact, the two things. One is that the input size x is n, and the second is that we have only, if you look at hardcore functions, then we only have order log n copy hardcore functions. Okay, we don't have bigger ones, right? So, in fact, this is also in some sense a lower bound, right? Like, sorry, an upper bound. That is, we cannot have larger than O of log n output hardcore functions, because if you had longer, then that would have actually appeared in the denominator over on n. Say we had log square n size hardcore function, then we would have had an n over log square n copy sv-OWSG that would have sufficed, right? But now we know that below that would not suffice, and therefore it also, in other words, means that we cannot have more than log n output length in a hardcore function.
Okay.
So it basically comes from the output length of a hardcore function. Okay. All right. So let's go to the next thing. Okay, now let's recall the Hill construction, right? So our construction is basically based on this construction by Hastad, Impagliazzo, Levin, and Luby. So let's say, suppose we assume that f is actually a one-way permutation, okay? And let g be a hardcore function, okay, of output length, say. So we'll always take, let's say, g to be of length order log n, okay? Now, consider these two distributions, P and Q, okay? What is it? So x is drawn uniformly, the input to f of x is drawn uniformly. We have f of x, R is another random uniform string of the same length as x, and g is hardcore function, okay? So what does it mean? By the definition of g being a hardcore function, it means that this f of x r g of x comma r is indistinguishable from f of x r and uniform in the length of uniform string in the length of output of g, right? That is by definition the meaning of a hardcore function, okay? So we get that this P and Q are indistinguishable. Okay, so R need not be exactly the length of x, but it doesn't matter. It's the input that G uses. Okay. Now, so if F is a one-way permutation, so F is injective. What does this mean? This means that the entropy in this, if you look at the entropy in P, right, it's exactly the entropy in X plus entropy in R, right? Whereas the entropy in this f of x r is already entropy in X plus entropy in R. So this G X comma R does not bring any additional entropy, whereas this uniform in the length of G, the output of G, brings in additional, say, at least log n entropy, but okay, at least one for now. So which means that entropy of Q is at least entropy of P plus one, okay? And hence P and Q are statistically far. And also, of course, we can see that they're both efficiently sampleable because, you know, f of x, generation of f of x is efficient, G is an efficient function to compute, and all of that stuff, okay? So this gives us a construction of
Statistically far just means non-negligible.
pardon me?
Statistically far just means non-negligible total variations.
I think in fact you're close to one, huh?
So sorry, just 1 minute. I am just trying to
In this case, it's actually close to one. Because you can tell the number.
I think it's something in here. I'm just trying to get back to the view where I can see the. Okay, doesn't matter. Yeah, sorry, Prasad, what was the question?
No, statistically far actually really far. It's actually constant far, not just non-negligible far. So the total variation distance is actually.
Yeah. But no, yeah. But you can boost the difference, right? Because you can.
Already close to one as per I was thinking, because GXR is support on a very small subset.
Yeah, exactly. It is like a sort of a half, much smaller support, right? So it's really far actually. Okay. But we can note one thing, that this really required f of x to be an injective function. Okay, this argument.
Okay.
So what happens if we don't have injectivity, right? So we sort of introduce injectivity, right? Just give me a second. I'll just switch on the light. Yeah. So if we have to introduce injectivity, what do? What we do is we take an extractor, right? So let H be a seed to a seeded extractor, and the output be H of x, okay, which is like an L bit output of the seeded extractor. And we consider this function xh goes to f of x, h, and hlx, right? So what does this do? It basically extracts the residual entropy in x given f of x, right? And therefore, it sort of makes this function an injective function, okay? xh to f of x, h, hlx. And in order to get, sort of extract almost all of the residual entropy, we want L to look like the entropy of x given f of x. But we also want to ensure that this remains a one-way function, right? So we want, in order to ensure that this remains a one-way function, we want this f of x h HLX2 be indistinguishable from f of x, tensor h tensor uniform L bits, okay? And this basically tells us that L, we cannot extract more than, this S2 of x given f of x. Now, what is S2? S2 is this collision entropy, or the Renby true conditional entropy, okay? So, as such, extractors can only extract, if you want uniform output, they can only extract up to this S2 of x given f of x bits. So in order to, we require S, but we can only get S2, right? So we basically want S to look like S2. But in the classical case, we are fortunate because, X condition on f of x is flat, right? Because x was uniform and f of x is a deterministic function, right? So condition on the function output, the conditional distribution of x is still uniform in its support, right? And whenever we have a uniform distribution, S is equal to S2 and it's equal to every other Renby entropy, okay? So as a fortunate consequence of that, we get that S equal to S2 for free. However, we have to ensure that L, because we are extracting depending on f of x, we can only extract, as many bits as S2 of x given f of x. So L sort of depends on f of x, right? And finding L from f of x is not necessarily efficient, okay? If you have a fixed output string, then we don't exactly know what is the size of its preimage, right? So L will depend on the size of the preimage, and that we don't know. So, so he'll handle this issue, this non-uniformity of L, via some intricate and elaborate arguments, okay? So, is this clear? What is this, way of going from a one-way function to sort of a one-way permutation by appending this extractor output? Any questions so far?
No.
Okay. So let's move on. So once we appended this, right, how do we get an EFI? Again, we do the same thing. We now append the hardcore function, okay? All right. Now, because we have sort of made, okay, so because G is hardcore, we get that P is indistinguishable from Q. And we have sort of made this function injective. So therefore now P and Q are statistically far, okay? And it's easy to see that they're also efficiently sampled. Okay, now that is the way to get an EFI. And the way to get a pseudorandom generator is basically, take multiple copies of this X, H, and R, take another seed S, and just put another extractor on top of all of this, okay? X is another seed extractor. And this sort of ensures that if you're using the right length of the extractor output, then this output X is a uniform distribution, okay? Which is what we want in a PRG, right? However, determining this T is not efficient, okay? And this is also handled by the stretching the output of PRG, which can be done in the classical case. Okay, that's how it is done in the classical case. Now, in the quantum case, one obvious issue is that we cannot condition on a quantum state, right? Remember, we were, this entire argument was happening conditioned on f of x, right? L was being determined conditioned on f of x and so on. So f of x is quantum, so it cannot be done. Okay, so that's the first problem. Okay, so now let's look at the construction of EFI in the quantum case, right? So we have the input security parameter lambda and a bit B. K is this advice string to the imbalanced EFI. And as a subroutine, this uses this mcopy sv-OWSG, okay? And let this tau xqm, so these registers, sometimes I'm going to use the registers on top of a state to just specify the registers. So this is the state that is generated once we use this OWSG, okay? And q to the m means these are the m copies of f of x in a sense, right? And x is the input. Now, we do that, okay? Now here, I'm just going to describe the construction, right? And then later we'll see why, these different things make sense. So like usual, similar to Hill, what do? We append this HHL, right? And also this RG, okay? And this is, okay, so firstly, we got to define the state tau 0 IL. Okay, what is that? I means how many copies of Q that we're taking. So Q to the I, that means Q copy of f of x in a sense. And L means it's the length L output for the extractor, okay? What we're going to do is we're going to mix this over all I and L, consider this mixture. And then we're going to do is we're going to take some T, okay? Some T, which is polynomial in n and lambda. Consider like T copies of row 0, which is this. And we're going to put an extractor on top of it. Now, this is the quantum extractor, okay? Quantum extractor, which can take as input a quantum state. And then, if B is equal to 0, we're going to output this object. If B is equal to 1, we'll just output uniform state in this 4 and not T plus 1 qubits. Okay? So this is the construction. Any questions on the construction?
So what is the quantum hardware function? So what is it supposed to do? So X and
Quantum basically, so let's say if you're looking at 1-bit output, right, then inner product is a hardcore function in the classical case. So the same thing also works in the quantum case. Okay, so basically the same constructions work. Inner product is also secure for quantum adversaries and so on.
In the classical case, I just want the output to be encrypted. So in the quantum case, what is it? It's a state which is close to being mixed.
No, I
close to being uniform.
think it's still a classical thing. There is hardcore against quantum.
No, but then tau 0 IL is supposed to be a state, right?
Oh, okay.
No, G is a classical function.
G is a classical function. Oh, same against one. Okay. But
Yeah. G is a classical function.
And for some basic state of that. So GXR tau just means that a corresponding basis state for that output. Is that what it means?
G.
So tau L is supposed to be a state.
Yeah. No. Sometimes what I'm going to do is I'm going to just write a lot of registers like this, right? But they're all the registers in tau. Okay, some of them are classical like H, HL, G, or they're classical registers. The only quantum register is this Q, or Q to the I.
Basic state has been there.
So in a sense, it's like a classical quantum state, CQ state, right? Bunch of classical registers, and this Q is basically the quantum register. When I say Q to the I, it means that these are the I copies of the f of x. Okay. All right. So, okay. Now, so we already like 50 minutes into the talk, right?
Yes.
Okay. So I don't have much time for getting into much technicality here.
You have 13 minutes.
Huh?
You have 13 minutes more.
13 minutes more, right? Okay. So, all right. So what I can say here is that, we cannot work with, conditioning on the output state, right? So we got to use these kind of, um, you know, these conditional, uh, these conditional, how should I say, this S2 of X given Qi, which are defined, with quantum conditioning, okay? And in order to get, S being close to S2, we have to use this idea of flattening, okay? That idea is sort of as follows, that you, divide your space of eigenvalues into these slabs, which are like all the eigenvalues between, factor of 2. And if you consider any such slab, it's a flat state or nearly flat state. And that is what you use to argue that S is close to S2. And because we need for conditional S2, we got to do more, which is, flattening after conjugation. Okay. And we also need, that sort of gets us something like S2 of X given Qi is the same as S2 of X given S of X given Qi. But we need S2 of X given Qi star plus 1. Okay. And that is because, in order to ensure that that where should I put it? Yeah. In order to ensure that after we have appended this H, right, there's still a one-way, an OWSG, okay? We need L to look like S2 of X given Qi plus 1, right? And that is because this verifier acted on this additional copy. Okay, so I copies were given to the adversary, and this verifier needed one additional copy. And because of that, we need this I plus 1 thing here. Okay, so essentially we want S of X given Qi to look like S2 of X given Qi plus 1. Okay, so all this requires some work, and in fact, that's our key technical contribution. So we are not able to show this for the original state tau, but we are able to identify a good substate gamma of tau, okay, where we are able to get the desired properties, and it's a good substate with a good value of Q here, and then we are sort of able to move to the desired, okay. So I don't have time to get into all this stuff. Okay. Now, the other way around, which is sv-OWSG from EFI, okay. This requires, okay, I just get my charger because my laptop is getting discharged. Just 1 minute.
Sometimes there is some this talk is announced late or one like wait, it can be. It was not exactly what happened for this one, but things happen. You know, people have to.
All right. So now in order to get the other thing, this is more straightforward. So what we can do is we can take an EFI pair row 0, row 1. And once we have X, we can generate phi X as basically, so let's say it's n bits, right? We can just generate it as row X1 times row X2 times all the way up to row Xn, where X1, X2, Xn are individual bits of X, okay? And now our verifier could be as follows. So let's say, because it's an EFI pair, so let's say row 0, row 1 are very far from each other, and there's this distinguishing measurement pi 0, pi 1, which is an optimal distinguisher for row 0 and row 1. Now this need not be efficient, okay? So this makes this verifier inefficient potentially. And then what verify does is just measures according to these projectors, right? So it basically tries to identify whether it is, if given an X prime, it just, just tries to do this optimal measurement, which distinguishes for each bit of X prime between row 0 and row 1, okay? So it just projects onto pi X prime 1 tensor pi X prime 2, pi X prime n for the bits of X prime, and this and I minus this. So it accepts if all of these things go through and rejects otherwise, okay? Now, this essentially gives us what we want. So because row 0 and row 1 are far away, therefore, the verifier will accept X and phi X because it's just doing the optimal distinguishing measurement. And if an adversary wants to fool the verifier, it must, sort of better output X prime equal to X, because anything other than X is pretty much rejected by this verifier. In which case, what the adversary is doing is pretty much, sort of guessing the bits of X, okay? Which is basically meaning that it's able to distinguish row 0 and row 1, okay? So therefore, we are able to, using this adversary, able to distinguish row 0 and row 1, okay? All right, so in summary, we show that an order n over log n copy statistically verifier OWSG are equivalent to EFI. This implies also, of course, that OWSG, from OWSG we can get EFI, because from OWSG we can get this order n over log n copy sv-OWSG, which gives us EFI. And this also provides an alternate proof, alternate construction, and an argument to Hill in the classical case, because we're not arguing conditioned on f of x. All right, and one open question that I can mention is to basically try to get that one expanding one PRS that I mentioned in that graph, Sattar's graph, which is sort of quantum equivalent of pseudorandom generator from OWSGs. Okay. All right, thank you. Let me just stop here.
Okay, thank you. Questions? Also, there are some people who will Zoom, right? Yeah. Questions from here over Zoom or in person.
Where did the n by log n show up? So when you're doing the other way from
Oh, n over log n shows up because let me go here. All right. So firstly, we are doing this identification of an index I star. Okay. All right. Now, here, yeah. Okay. We want to find this index I star such that this S of the entropy of X given Qi star is nearly the same as entropy of X given Qi star plus 1. Okay. Now this we want nearly the same means up to additive log n, because that order log n we can cover up using the hardcore function. So we want this to be nearly the same up to additive log n, right? So now entropy of X is varies, from 0 to n. So that's basically n, right? So the conditional entropy will vary from 0 to n. So therefore, if we have, n over log n coordinates, then we will get a coordinate where this difference will look like order log n. Okay. Yeah. Right. If you have smaller number of coordinates, then this difference would look larger potentially. But if we have at least n over log n coordinates, then this difference will look like log n. So that is where. And why do we want this difference to look like log n? Because log n is what is the difference that we can cover up using G. Okay, that's the most difference that we can cover up using G. So we want that to look like the difference to look like not more than log n, and that's where n over log n comes from.
Okay.
So the original kill proof,
Yes.
subsequently made simpler by these works of inaccessible entropy, pseudo entropy in crypto works. How different is your alternative proof from theirs, and is the final result the same, or you get a weaker result than their alternative proof?
Okay, so
this is all in the classical world. You claimed in the
yeah, so we haven't really looked into these newer results and what are their parameters. And also in the classical case, we haven't really pinned down the parameter. Like we haven't really exactly looked at, the running time and everything, so as to compare how efficient those constructions are versus how efficient this construction would be. But I mean, conceptually, proof-wise, this appears simpler than hell. What we could do is, which we are planning to do as well, is to actually write down like a proof sketch for the classical case, and then maybe compare explicitly with these parameters that the newer constructions get. Yeah. That might be helpful for the classical guys. I mean, I think Pranav has a question.
Yeah. Can you elaborate a little bit on the good substate and the flattening? I think I missed that part.
Okay. So, all right. So we want this thing, right? Eventually we want something like this, right? We want S2 of X given Qi star plus 1 to look like S of X given Qi star. Okay. Now that we are not able to argue in the original state tau, okay? Because Pranav, one can imagine, right? If you want to make S2 close to S, you sort of need some kind of flattening, right? You want NV entropy to be equal to entropy, so you need some kind of flattening, right?
Yes.
So that is the flattening that is achieved, okay? And due to that flattening, I mean, okay, one way to achieve flattening is, you take this, for example, you want to flatten a state tau, right? What do? You take its eigenvalues, right? And you divide into slabs, right? Where let's say you have a factor of 2 gap in each of the slabs, right? And then if you consider any slab, it's a flat state, right? So that can achieve flattening. And once you have flat state, then your NV entropies are pretty much the same as your entropy. But also you need flattening not just of the state. I mean, you just don't want like S2 to be like S, but you want conditional S2 to be like S. And therefore you want to sort of flatten that state in a conditioned manner, right? So you condition it on it. This is the conjugation that sort of achieves conditioning. And once you condition on it, then you flatten it, okay? And then you consider these, eigenvalues of this theta, make slabs out of it and generate J. And then if you condition any J, then you will get that this conditioned entropy is like entropy, okay? But then this gives you that the S2 of X given Qi star is like S of X given Qi star. But what you need is, in addition, S2 of X given Qi star plus 1, right? So therefore, we need to further go into a substate of tau j. This just tau j itself is not also enough, right? These slab states are also not enough. You got to go to another substate of that, appropriately identified, and that is able to achieve this.
Okay, and I mean the containment parameter is like 1 by log n or something.
Oh, the container is 1 over poly.
1 over,
1 over poly.
1 over poly.
So,
Yeah.
Pranav, we are not able to hear you well.
Yeah, Pranav, can you speak a bit louder?
Let me try a different microphone. No,
Now it's working. Now it's working. Yeah.
No, I just used the system microphone. Yeah, I think I follow largely. So it's to add in that +1 register that you are somehow, I mean, it's not fully clear here. You are looking at the substate. Like, is that right?
No, substate would anyway be needed. Even if we didn't need +1, the substate would come because we need flattening, right? Because even to just ensure this, for example, S2 of X given Qi as S of X given Qi, right? That itself will require you to take one of those slabs, right?
Yes.
And the point is you can ensure that the number of slabs is only poly, right? Poly in n, because you're doubling these eigenvalues, right? So therefore, if you take one of these slabs, it will give you good weight, okay? But that slab is not enough. That only achieves this, okay? S2 is close to S for X given Qi. But X given Qi plus 1 requires you to go further substate of that slab.
Okay. Yeah.
Okay.
Yeah.
So that's what happens. Yeah.
So that means your quantum states, you're not taking the original quantum states of the generator, but you are taking the flattened versions. Is that right?
No, what you do is, you see, if you go to a slab, right, it's a substate. Agreed?
Yes.
And you go to further substate of that. So essentially, you identified some substate where you're getting your desired properties. Okay. Okay.
Okay.
Now, what do you do? Once you have that substate, what do you do? What you do is, okay, so once you have these desired properties, if you just look at gamma, suppose gamma was your state, right? And you appended this RGR, RGX, R, you would have got your EFI pair, right?
Yeah.
Because that was everything nice was happening there.
Yeah.
But that's only happening for a substate, right? So what do? What you do is, okay, so let's call these, if you have gamma, then this kind of EFI pair that you get, let's call them sigma 0 and sigma 1, okay? Yeah, with this H and this G appended and all that stuff. So you've got sigma 0 and sigma 1, okay? Now what you do is, you see, you would have originally tau, right? So what you do is you do this appending for tau, this H and R, okay? But what is happening is, okay, so this should be actually Li star. So this there's I star, but this should also be Li star. So what's happening is that once you append this, it looks like that for substate, right? You appended it correctly for sigma 0. And so let's say your tau splits as q times gamma plus 1 minus q times theta, right? Now, so this is the right appending that's happening here. And in theta also, this is the right appending. That's happening for tau 0. But for tau 1, what you want to do is you want to replace this substate part by sigma 1, okay? But this theta part, you want to leave it as it is, okay?
Okay.
You want to leave it as it is. Now, the sigma 1 that you get is the one where you have sort of replaced this G by uniform, right? Uniform bits. So what you're doing is only in the substate, you're replacing by uniform bits, okay? The rest of the places, you leave it as it is, okay? So now this gives you another 1 over poly hit, but then still you have this entropy difference to be 1 over poly, okay? But because sigma 0 and sigma 1 are indistinguishable, and these are anyway indistinguishable because this is exactly the same state, your tau 1 and tau 0 also become indistinguishable, okay? So this is how you get for the original one, you can argue that there is both entropy difference and they're indistinguishable. You go to the substate, make the argument there, and then appropriately create this tau 1 tilde. Okay?
Okay.
And then this I star Li star is what you don't know, right? So what you got to do is you got to average it over, okay? So you mix the whole thing, okay? For all I and L. That's how you create rho 0. And rho 1 is again the same thing, except for I star Li star, you take tau 1, okay?
Okay.
So now again, rho 1 is what you don't know. Rho 0 is fine. Rho 1 is what you don't know, right? So now you sort of tensor it multiple times, okay? T times, and then apply an extractor on top of it. So then eventually rho 1 tensor T goes to uniform, and rho 0 tensor T goes to some state which is far from uniform. If you're okay, so once you apply this extractor, you got to look at how much seed length you have to provide to it, right? So the seed length is sort of large enough, which is k less than a k star, then you get that these things are indistinguishable. But if the seed length is small, then this, in the rho 0 case, you get something that's far from uniform. Okay. So that's how you get this imbalanced EFIs, and then you take these imbalanced EFIs and then get EFI using construction from KT. Yeah.
Okay. Thanks.
So I my question was something very much higher. So this conjugation in the classical case will look a little bit like conditioning, right? So you're dividing one probability distribution by the other, and so the zeroing out wherever is there. So is that what's
So I cannot hear. Can you say again, maybe?
No, so this conjugation is what is playing the role, because it's like it's sort of like you're zeroing out the part which is not the support of the conjugating state, and on the remaining looks like conditioning. So if it was a classical distribution, it looks exactly like conditioning. Is that?
Yeah. Right. I mean, the classical case, for example, right, when you want to consider conditional entropies, you divide by the probability of y, right? And that is the division. That is that to the minus half conjugation. That is the division. Yeah.
Just one more comment, Rahul. This regarding the classical proof of Hill, especially given that a lot, like Iftach Heitner's, there are at least 2 to 3 papers that I know in which he talks of them as hill climb being made in D. Okay.
Yeah.
So, and they actually use a lot of ideas from information theory. That is, they have defined these terms called inaccessible entropy, pseudo entropy, and all. I remember all of this one.
Pseudo entropy, false entropy, and all also. Those things were there in Hill also. Yeah.
Inaccessible entropy was a new thing. Whether I would just be curious from how different is that proof from your proof.
Yeah. We should look at it. We haven't really looked into those newer proofs. But
Okay.
Okay, I mean, firstly, there is no conditioning on f of x that we are doing. Okay, so that is already, a key point of difference from Hill. Now, I don't know whether these other classical proofs are working condition on f of x at all or not. Firstly, right? Because I mean, we don't work condition on f of x. So that is one key point of difference. I mean.
Okay.
Okay, thanks. Thank you.
Okay, thanks.
Thanks, Rahul. Bye.
Amen.
Okay.